So in this lecture, we will go through the complex representation of waves. And as a brief motivation, the point, why do we want to go into describing waves instead of sines and cosines with the complex numbers? Well, there's actually quite a few of good reasons. The mathematics really becomes more easy to understand and treat with. But if a single main advantage would need to be highlighted, I would really say that it's the phase function and its treatment that becomes way easier when we're dealing with waves using complex representation. So it's really the kind of phase function, how the waves evolve and how their phases are evolving during propagation or during evolution of time, that is considerably simplified when we go into description of waves using complex numbers. And in this lecture, I will go through the basics of the mathematics that we will need to subsequently do in order to treat waves accordingly. So I will show you briefly what are complex numbers. I will show you that they're using exponential functions and complex numbers. We can easily treat wave-like quantities, and I will speak about the complex number z, its real part, its imaginary part, and I will introduce how we can understand this complex number to be lying on a complex plane, and subsequently how its imaginary part can be understood to be giving rise to the phase of the number. So I will be introducing to you the phase angle of this number, complex number z, and I will be showing to you the Eulers formula, which is a very important and useful formula to describe these complex numbers. So in case you are not already familiar with Eulers formula, please memorize it during this lecture or after this lecture, or at least do your best, because it will be helping you quite a bit during your journey in our university. And hopefully also later on in your life. It's a highly useful equation. And then finally, I will be showing how we can add complex numbers together, how we can subtract them, and how we can multiply and how we can divide complex numbers using the exponential notation. And then finally, I will be showing to you how we can calculate the amplitude or the length of a complex number, which then in our case of waves physically represents the amplitude, the strength of the field. So this is what I will be speaking about during this lecture, and I will now start. I hope you enjoy the ride. This is a very good prelude for the further description that we will be having of waves in our course. So until now, our mathematical description of waves has really been based on sines and cosines, as you remember. So we can already describe harmonic waves, so waves that are propagating in space, and we have used a simple sine formula, sine equation to treat these kind of waves. And this is of course nice, there's nothing wrong about it, and it works quite well in simple situations. But when we start treating things that are a little bit more complicated, and especially in derivation of things, it's really the complex notation that helps. And this is a more general way of treating waves and wave motion, and this is the reason why we do it. So in the end, it might be the case that you are not as familiar in dealing with complex numbers, but in the end, this will be way easier. And in case you're not very familiar with complex numbers, don't be afraid. We are not going into a complex analysis, so we don't need to treat about subtleties of complex numbers in the complex plane and how we could treat analytical functions and how we could generalize analytical functions into the complex plane. So what I'm trying to say here, we're mostly dealing with addition and subtraction of complex numbers and multiplication and division of complex numbers. And we do not need to, for example, worry about integrating a complex valued function or differentiating. Okay, differentiating, we will need to do that a little bit, but at least we do not need to go into the kind of complex analysis of things that you would encounter if you would go into a course in the math department focusing on complex numbers. So just simple, rudimentary, basic information, just the fact that you know that there are such things as complex numbers, that's already enough in the framework of this course. So let's get started. We have a complex number, z or z, and my apologies, I'm not a native speaker, so it's all the same to me, potato or potato. So z or z, sorry about the hassle regarding using different ways of saying the same thing. We can divide always this complex number into its real part, and most of the time we describe that with x, and the imaginary part, and which we describe using y. And of course, mathematically, how we connect these real part and the imaginary part to form a complex number z, we can write this simple equation so that the z complex number consists of its real part, x, plus the imaginary part, and we multiply the y with this imaginary unit. And one way of defining I would be that it's the square root of -1. Graphically, we can describe our complex number z in the complex plane. So then in the x-axis, we will draw the real part and real numbers, and into the y-axis, we will then expand our imaginary numbers along this direction. So y-axis will be the imaginary part. And then complex number z corresponds to a single point in this 2D space. And then our phase angle here, theta here, corresponds then to the kind of phase of this complex number. And in the future, we can really connect this phase angle of this complex number with the phase of our wave. So this would be the kind of physical connection. In future, sometimes we also need to be calculating the complex conjugate of our complex number z. So then we use the notation of having star after the z, and this graphically corresponds to the case that we just reverse the imaginary part of our complex conjugate. So the real part remains the same. We just flip the arrow to be on the negative side of the imaginary, part. So this is how we define our complex number z, and this is how we progress. And of course, we can either think of our number z as a point or vector in the complex plane. So complex plane often is being denoted with this kind of cardinal C letter. and this complex plane, of course, is a 2D plane, 2D space defined by the real axis and the imaginary part. So in that sense, it's a two-dimensional plane. And the coordinates, of course, can be written using this kind of notation, so that the real part x equals r. This is the length of our complex number times cosine of the phase angle theta. And the imaginary part similarly can be written that it's the amplitude r of I complex number times the sine of the theta. So r here is the length of the vector, or length of the complex number, or amplitude, and the angle theta, the phase angle, is essentially given by the arcus tangent of y per x. So that that's how we define things. And here we have the angle theta, and then of course we can see by just drawing a triangle here that indeed these equations do make sense, as long as this r is the length of my vector pointing to this point z in there. So simple equations and simple math, but in case you're not familiar with this, it would be good for you to try to memorize things, because we will end up using these all the time. Not on just this course, but in most of our courses in physics from now onwards, because most of the time we're dealing with wave-like quantities. For example, electrons inside a solid piece of a material in the framework of solid-state physics, or condensed matter physics. Of course, we're in the end dealing with waves. And now Eulers' formula. This is a very useful and highly important formula. We can connect the z with an exponential notation. So the z, the complex number, can be written that it's the length of this vector times inside the parenthesis of cosine of the phase angle theta plus I times sine of theta. And this thing here, this cosine plus I sine, where we actually do have the phase information of the wave, we can actually simplify using an exponential notation. So this is now simply written the z the complex number as r times exponent to the power of, exponent I theta. And the complex conjugate of z, so z star, can be similarly be written. So it's the r times cosine theta minus I times sine theta. So now we just replace the plus sign here with the minus sign because we just wanted to flip the number with respect to the imaginary part. And then simply we just have a minus sign here in the exponent when we want to calculate the complex conjugate. And this is quite nice because this is very quickly written, and also we can deal with the kind of properties or take use of the properties of the exponential function to then deal with the calculations. So for example, when we want to add waves together, or in case we would want to multiply phase together, for example, to calculate the modulo square in order to calculate the amplitude, the strength of the field. So this is how it goes. An Eulers formula, it's very useful. Please memorize it in case you already are not familiar with it. And now what we can do is that we can calculate what are the sums and differences. So how do we add numbers and how do we subtract complex numbers from each other? So let's define two complex numbers, z1, and then the real part of this number will be denoted with x1, and the imaginary part with y1. And in this exponential notation, the length of this complex number would be r1, and the phase angle would be theta1. And similarly, the second complex number z2, and subsequently same kind of sub-indices of 2's everywhere. And now if we add or subtract these kind of two complex numbers from each other, we can just deal this kind of operation easily using the normal notation. So we just sum or subtract the real parts from each other. And similarly, we either sum or subtract the imaginary part from each other. So simple as this. The multiplication and division of numbers, complex numbers, can also be easily done, but it's easier to use the exponential notation, so the polar form. So when we multiply two complex numbers together, z1 multiplied with z2, then we can multiply the amplitudes r1 with r2, and then we have the phase angles, and we just add the phase angles together. So this is how we can deal with things. Physically, I would want to highlight here that in this framework we have for this course, we're really dealing with so-called linear optics, and we do not need to worry about very, very strong fields that would be also interacting nonlinearly with the material. We do not really need to multiply complex numbers that much together. Like if something we need to do, we need to multiply a complex number with its complex conjugate, and these kind of calculations we need to do. But in most of the physics we're dealing with in this course, we do not need to multiply two waves together. We add and we subtract waves together so that we do that kind of mathematical operations, but we do not multiply or divide waves from each other. So physically, what I would say is that the superposition principle really applies in all of the physics that we are dealing with in this course. That's not always the case in physics in general, but at least in this framework of this course, that's what we have. Okay, let's continue. The division of complex numbers can easily also be done using the exponential notation. So dividing z1 with z2, we can just divide the amplitudes, so r1 over r2. And in the exponent, we now just subtract the phase angles, so the phase functions of the waves, when we would be treating waves using complex numbers. So this is quite easy operations, and we can do these in case we need. And the kind of only thing left over is that let's calculate or come up with the way of calculating the length. So what is this r in each of these complex numbers, and what would be the kind of modulo square of the complex number? Because then when we are treating waves, this is actually something that gives us a value that we can then measure in real life. We can measure the amplitude of the wave quite easily, not the phase. So the length of the vector, of course, we can calculate the modulus square of the complex number z, and how we can do this. We can, for example, do it by just multiplying the complex number with its complex conjugate, mathematically, using the exponential notation, we can write it like this. So basically, the only thing we do is that we have the exponents I theta and I minus theta. They, of course, like vanish. And what we are left over is that we have the x squared plus y squared here. So this is like how we can calculate the modulus square of the vector. So there are many ways how we can calculate it, and please be familiar with at least one of these ways so that you can do the calculation when needed. And if we have a complex number, and if we would want to come up a way to calculating the real and imaginary parts of this complex number, we can easily calculate the real part of the z using, and this is of course denoted with x. We can calculate it, for example, using this equation. So we add the complex number z with its complex conjugate and divide it by 2, and this is what gives us the real part of the complex number z. And similarly, the imaginary part of the complex number z, and this would be denoted with the y, we can then calculate by just subtracting the complex conjugate z star from the complex number z and divide it with 2 times I, the imaginary unit. So these are the equations that we can use to calculate, for example, the real parts, imaginary parts. We can calculate the length, and we can now also just add, subtract, multiply, and divide complex numbers. And this is pretty much all we need to do in terms of mathematical operations. And now let's just move in our treatment to actually use these complex numbers to describe physical waves. So this is what we will do in the end of the lecture. So let's start from the harmonic wave. So we have the psi depends on 2 variables, so it just propagates in one direction. Z is the propagation direction and it oscillates in time. So we have the amplitude of this wave, so we have the A, and then we have the phase function, so we have a cosine, or it could be sine, but just cosine here, and we have the kz minus omega t plus epsilon, the initial phase inside the argument. So of course, this guy here inside the cosine, this is our phase of the wave. And this is the guy we need to be hiding inside the exponent in order to represent things using the exponential notation and complex numbers. So we can calculate this and of course the difference that we have here is that this is a completely real valued number. So as long as A, the amplitude is real valued, like the outputs of a cosine, they will be real valued. So when we need to go into the exponential notation and complex numbers, like mathematically, if you want to have equality here, we must take a real part of a exponential complex number, exponential in this complex number. And the equality stands as long as we take the real part here, and then we have the phase information written using the exponential notation, and we have the imaginary unit here. So this is the kind of notation we will be using a lot in what follows in our course. And here, the real part, of course, can be calculated by just adding the complex number with its complex conjugate, z star, and divided by 2. So then, since we know that this is the real part of this complex number, so we can take use of this equation, and then we can write that this wave can also be written, it's 1/2 times the amplitude times exponent I kz minus omega t plus epsilon, and then the complex conjugate, so 1/2 times the amplitude A times exponent now minus I and the phase function inside. So basically just we're using this to write the real part as this. And this doesn't look very nice, because just writing things using cosine would be simpler. But what we can do is that we can just simplify this, and we can forget the fact that in the end we would be taking the real part, and we can just use a single term like this to describe the wave. And then we just remember that in the end, if we would want to have something that we physically measure, we just would take the real part of our complex valued wave representation. So psi in practice will be written, and this is the notation we always use in optics and photonics, is that we can write it with the amplitude A times exponent I and then the phase function. So kz minus omega t plus epsilon. And let's just simplify or clarify the meaning of these terms in case it's not clear. This first term, kz, this is the term that gives the phase evolution when the wave is propagating along the propagation direction z. K was the amplitude of our wave vector. So k tells us how quickly it evolves. K equals 2 pi over lambda. So here, depending on the wavelength, the phase evolution is different. And then omega, that's the angular frequency, and time is the time that progresses. So this term here gives us the evolution with respect to time. So how the field oscillates when time evolves. And angular frequency, it's connected to the normal frequency, that the omega is 2 pi times the frequency, f or nu, so that we see that when we change the frequency, then also the oscillation period changes with respect to time. And epsilon was the initial phase that most of the time, like we can just keep that to be a 0, but in some cases we just need to have something that is not 0 anymore, especially when we are summing different waves together and we're kind of locking our problem to something specific. And here, this initial phase, we can also hide that away inside the amplitude. So instead of using a real number to describe my amplitude A, I can also just hide this initial phase into the amplitude. And then to just clarify this, I will use a prime notation here. So this A prime now is actually complex valued number. And then the rest inside the phase argument will be kz minus omega t. And here, the complex amplitude A prime, of course, we just defined that it's the real valued amplitude A times the exponent I epsilon. And then here we have the initial phase of epsilon included. So this is also possible, and please remember this in what follows, that the amplitude can also be complex valued in this notation, and then it would just mean that we have some kind of phase related with the field. That if we would want to describe the phase, or we would want to change the phase at the origo of the given coordinate system for the wave and the treatment. If we would want to change the phase at the origo, then we would need to change the initial phase, and that can be understood, or that can be done also by just using complex amplitudes instead of real valued amplitudes. And now the only trick, and we don't really need to do this trick that many times in our course, but if we would want to kind of really have a description for the wave that makes physical sense, we would just take the real part of this function, so that we would get something similar to what we started with. So this is what we will do in the end. But I will be speaking about this later when we are going into the treatment of Maxwell's equations, because there we will be defining what is the electric field and what is the magnetic field. And then I can actually say to you why physically we want the electric field to be a real valued quantity. So that there I will try my best to explain to you why we actually are interested in real valued quantities at the end of the day, and not just complex numbers. But in the end, complex numbers highly useful when we are describing waves. So consider them as your new friend and not as your enemy. And I think that is the kind of key to success here. So thanks for listening this lecture. And next we will be generalizing our treatment. So we will be progressing, and we will be using this exponential notation and the complex numbers to describe plane waves. But of course that will be in the agenda of the next lecture. So thanks for following, and bye-bye.